We will talk today about energy transfer of motors and the electric engineering artwork behind that. At the end of the day, it is what it is, but is there a lot of energy transfer within motors? The law of conservation of energy states that energy can neither be created nor destroyed, only converted from one form of energy to another. So the electric energy used by a motor is not 100% transferable to a mechanical motion. Most of loss on this energy transfer is associated to heat. The heat generated by the electric motor is distributed throughout multiple components within the electric motor. And you can feel when you put your hands over the enclosure of a running electric motor. This heat is generated due to losses within the stator slot windings, stator end windings, stator lamination, rotor laminations, and rotor magnets and conductors. There are two important factors associated with heat and power. The first one is efficiency and the other one is power factor. There is no motor on earth that have those values equal to 1. It is too ideal of a situation. In fact, this energy loss is worse on TENB motor type, which means totally enclosed non-ventilated. TENB states that the motor housing is fully enclosed and is not ventilated with a fan, similar as an explosion-proof motor, which are completely enclosed to withstand an internal explosion of gas or vapor. The table that you have here is an example of one AC motor manufacturer doing quick math of a 10 kilowatt motor. It has a loss of heat of 150 watts per kilowatt. So there are 1500 watts of heat loss. 15% of electric energy is transferred to heat and only 85% is transferred to a mechanical movement, torque and speed. This concept looks very basic, but it is going to be the pillar of future videos where I will talk to you about temperature ratings, stopper hours and duty cycle. All of them are associated within this energy transfer concept here. Heat and many of their design limitations too. Also, the standard IEC 634 states that when they mention the thermal equilibrium concept. Now that we understand what the energy balance equation on motor is, we can confirm that motor lost a lot of energy through convection heat. So why is all of this useful? Emerson's engineers took energy transfer into consideration when they sized most of these applications. Also, ambient temperature is important depending on the application. As an example, about 40 Celsius, 105 Fahrenheit per NEMA MG1, the heat transfer model breaks down. The motor can no longer transfer enough heat to the environment to self-cool effectively. As a result, the motor's operating temperature climbs and may exceed the maximum temperature for its isolation class. On top of that, every 10 Celsius, 18 Fahrenheit, rises above the isolation class limit cuts your motor's expected life in half. I mentioned all of this because the XTE 3000 sizing tool and our engineers took in consideration motor temperatures, motor types, and the rates motor to preserve your motor's life, reducing its loads so that its operating temperature stayed with its isolation class limits. The rating your motors depends on the ambient temperature as well as motor's isolation class, and its temperature rises at nominal or rated load. The XTE 3000 have different types of motors for different types of applications, and we will talk a little further about this in our next videos. In our next session, I will explain to you the importance of the temperature ratings and how it is important for actuators and valves. So I don't have anything more to say that thank you for your time.